very many, what we say, old school data acquisition tricks. For example, if you need the temperature of something somewhere, there's temperature stickers that change color on temperature. And you put the sticker on a place, you don't know what the temperature is. It won't give you the profile over time, but it will tell you what the peak temperature is without any electronics or any computers or anything. There's other methods for aero. For example, putting dots of oil spaced closely apart on an aerodynamic surface. You can then see how the air moves the dots of oil around without any electronics. You can then maybe take a photo and share it with the other team members, but that's fairly easy to do and it doesn't cost much money at all. Another thing, if you're worried, you have questions about the car hitting the bottom of the ground and you don't know where, you can paint the bottom of the car. Go out, let it hit, and then look to see where there's no more paint. And that will tell you where on the bottom of the car you're hitting the ground. It won't tell you how hard, and it won't tell you where, under what conditions, but it will tell you that you are hitting. Some other things, I was more focused on like program management and service and things like that. So what I wanted to recommend is, in general, when you go into a design judging, we have 45 minutes to judge you on everything that you show us. And so whatever you bring is what we see, what you don't bring, we don't see. And there can be many reasons for that, but unfortunately it's hard for us to judge on things that we can't see. So that's really important for you to share that with us. One way to get a little bit of a head start is to study the judging sheets, which are available to you. So you can see where we score, you can see what's important for us, and it makes it easier for us if you come in prepared to go through explaining things like this, because you know that's what we're going to be looking for. So in terms of program management, what I was looking for is how do you organize everybody's work to make sure that you're sharing information and you're following a schedule and you're meeting your plan and you're getting things done as you expected, rather than everybody who's responsible for a subsystem sort of off doing their own thing, and the sharing of information is very minimal and there doesn't seem to be a clear plan. So we're looking for information on how you do that, and so that it helps if some things are prepared for that. Another thing in terms of service, you'll see on the scoring sheet, some things we look for is interchangeable parts and common hardware. Now, you said we had common hardware, but looking at the car, there's quite a few different size fasteners, so it was difficult to understand what that might be. Providing a drawing of you that you already have, showing how the car is assembled and what the parts are, would be very helpful towards making that judgment. Something, also, I'm kind of old school myself, and it's easier for me if someone has something printed out versus going through their computer trying to find the right file to show it to me. And that's not you guys, that's kind of everybody, because it's more common for people to want to put everything on a shared drive, and then when we ask a question, rather than preparing for what we might want to know, well, everything's on the drive, we'll go find it when we're asked. And then that may take 5-10 minutes to go find what we want to see, which takes away from 5 or 10 minutes of getting more information from you guys on something else. So anticipating what we might like, and maybe a big assembly drawing of the car would be nicer and all the parts and stuff. My question of how would I put the car together? Here's how you put the car together, I would have liked that quite a bit. Another thing I didn't really ask you guys about too much, but in the past I've judged on the following of an engineering process. And what I mean by that is sitting back and say, you know, I'm going to design something. And this thing I'm going to design is going to have some objectives. It's going to be this big, it's going to withstand these forces, it's going to be this fast or whatever. Now I'm going to design this thing that meets these objectives. So you're going to show us those steps. And now I have the objectives. Now I'm going to build this thing, I'm going to prototype it, I'm going to simulate it. You're going to show me the simulation. But it shouldn't stop there, because the simulation is not what we call validation. It doesn't prove that it's going to work. So after you've simulated it, then you have the test data that says, well, it kind of worked. And that's okay. You've gone through the process and it didn't work perfectly, but you've gone through it and we know now that you guys know how to do a design process to design something. That's pretty much all I had.
Okay, so I'll talk about powertrain. Is it okay if I stand over here so
Yeah.
I can point to the engine? Okay. All right, good morning. Okay, so powertrain. So I usually ask a set of questions that go from big to small and move around all the subsystems. And so we'll just talk about those from piece to piece. But in general, what we're looking for in design, sort of the first level of understanding, the basement of understanding is you selected something and you built it and it runs. The next level of design understanding is why did you select that piece compared to all of the other options that you have. And then the final one is how you've selected the piece and what optimization that you've done in order to really make sure that the details inside of it are appropriate. So the first question I usually ask is, why this engine was selected. The answer that you gave was because of its cooling performance, which I didn't really understand. So maybe there's something in there, that was in the translation. But what I would like to see is we had all of these options, and we decided for a single-cylinder engine. Why not a 4-cylinder? Why not a 2-cylinder? Why not a 3-cylinder? So there's lots of options, and even hand calculations of power to weight ratio or cost, or something like that would be good justifications of why you selected this engine. So again, we just like to know, why. Every one of these things, just ask yourself the word why. Okay, 5 times. 5 times, right? So, okay, and then we also like to talk about why you selected the fuel you did. So there are multiple options in the competition. There's 93 octane, there's 100, there's E85. So again, your gasoline selection is one of the options. Why is this the right one for you? So some justification. Could be it's cheaper, it's easier to find. If you picked 93, we don't need 100 because we're not NOx limited. E85, alcohol fuel offers some advantages. It makes more power, it has more latent heat of vaporization, so it runs colder, and it has excellent NOx performance. So I'm always interested to make sure that even if you do not select E85, that you understand, the benefits of it. What I really liked, one really good thing we saw in the beginning was that you changed the engine from a carburetor to fuel injection, and you showed a power increase that was tested on a dynamometer. So a really big fan of dynamometer testing. I think, as everyone knows, there are many things and choices and design criteria inside of a powertrain where you must measure load in order to make decisions. You make this change, you measure load. You make this change, you measure load. You make this new design, you measure load. The best way to measure load, is usually cylinder pressure, but it's very, very difficult. The next easiest is an engine dynamometer, but not everybody has an engine dynamometer. The next easiest is a chassis dynamometer. Not everyone has access to a chassis dynamometer. But you can do testing on the track and make changes, and you can also look at manifold pressure. So manifold pressure is a really, really good indication of load and efficiency. So for a given torque and a given RPM, as the engine gets more and more efficient, you'll have more vacuum because it needs less air. So you can use the sensor that you already have as a cheap, easy dynamometer to make some of the changes, the spark and fuel, and see how the load and the efficiency of the engine changes. So even if you can't run everything on the dyno, it's great that you have one and you have data. Sometimes you can do simple things, as we had talked about, with other tools. Let's see, we talked a little bit about the drivetrain, and most of the answers that I got back on the differential were that it's the standard Formula Student package. So basically you're buying it and you're installing it. Again, the next level would be, how did we optimize what we bought? Different bias ratios, different preloads. Why did we pick the sprocket ratio that we did? You could calculate tractive effort, torque, force on the bottom of the wheel versus vehicle speed versus gear, and change the diameters of the sprockets to look at different gear ratios, right? So we'd like to see those calculations as well. And then the next level of understanding is, do you have finite element analysis on the strength of the bearing carriers and how much load, everything can take. That's sort of the next level. And then finally, on-track testing and driver feedback of how the performance of the differential brings the power to the ground, is what we really like to see in drivetrain also. You showed that you had a mechanical cable actuated clutch and shifter, which is fine. I competed in 1997, which is a really long time ago. It's like 25 years ago, and we won with a mechanical shifter and a mechanical clutch. So it can be done. But again, you need to understand what the trade-offs are for an automatic shifter, an automatic clutch, even a hand, integrated clutch assembly. You just need to understand the trade-offs and show that you're thinking about it. I really liked the 3D simulation of the intake manifold. So you had 3D CFD of this shape. When you're designing intake manifolds, it's important to do these calculations at different speeds and loads because the air does different things at different flow rates. So you showed me a picture of one speed load, and all of the flow is coming right down the backside. So then you wonder, why do you have all this volume, right? So when designing intake manifolds, we usually talk about it from one end to the other. So it'd be nice to know, how did you pick the air filter? Is it too fine or too coarse? How did you pick the throttle diameter? Is it too fine or too coarse? How did you design the restrictor to be the most efficient? And how does restrictor size and geometry changes affect performance? How do you design and select the volume of the plenum and the angles and the shapes inside? Because that affects performance. How did you affect the runner length? Is it tuned for a given speed? Are you trying? What are you trying to do? Shaping your torque curve. You can change the length of this and the volume of this to change the shape and the characteristic of the torque curve. And then similar things about the exhaust system. So the exhaust system on a single cylinder, not as sensitive as a multi-cylinder, but still the length of the pipe matters. And so we're interested in knowing, did you design the length of the exhaust system and the volume of the muffler, to help scavenging of the single cylinder, and then some calculations about the muffler. Did you buy the muffler? Optimize the muffler, design the muffler? Did you try different things, and have you measured the noise level? So those are the kind of, what we'd like to see for all the different parts. This kind of grade of understanding. Cooling system. So we talked about the cooling system a little bit. The feedback was you're targeting 86 degrees Celsius coolant temperature, which is a little bit cold, but you did say you're using water and not coolant. So if you're using water, we're also interested in knowing whether you're worried about corrosion. Are you adding an additive to the water so it's not rusting the parts, or corroding the aluminum inside? And then 86 again seems cold. The coolant temperature can move around a little bit, and if it's coolant, it won't boil until 115 or 120. So 120 is very far away from 86. So we're just wondering what you were thinking and why to run the engine very cold. Okay, so then we'll talk about the calibrations. So we looked at the spark map, spark advance ignition timing. It did not change with load. So we would expect an optimized spark map to have more spark advance at light load and less spark advance at heavy load. So the two big trends we're looking for in a spark map is retarded at low RPM, advanced at high RPM, advanced at low load, retarded high load. So it should be sort of a three-dimensional triangle shape. So there was a good trend with speed, but not necessarily with load. Fuel map, I looked at the fuel map. The explanation that the numbers inside the table were angle but they were sort of they looked like pulse width, like in milliseconds to me. So you'll have to, understanding a little bit more about the fuel map calibrations and why you picked, what you did is also important. So like we talked about, measuring load, as you change fuel settings and as you change ignition angle settings, the load of the engine changes. And at wide open throttle, you should optimize for, peak power or a balance of fuel economy. And then at light load, it should be all fuel economy. And the nice thing about this competition is that there's no catalytic converter, so you can run lean. So at very, very light loads, I rarely see it here, but you can run the engine lean without hurting it. You just need to watch the exhaust gas temperatures. Okay. And then, overall, again, I'll iterate the comments that Skidder said. We're, very, very happy that you were here. It was very enjoyable talking to you yesterday. Thank you for bringing comments pre-translated into English. That was really helpful. And next year I'll try to learn some more Spanish. Okay. I promise. Okay.
Thank you.
Okay.
Thank you very much.
Yeah, thank you. Yeah, and we can answer questions after the next people talk.
Okay.
Okay. Rich, do you want to do the systems or? Oh, okay.
¿Cómo es que dice que diferente?